Advanced Math, Set 88, Exponential Functions, Growth and Decay. Exponential functions are of this form, actually that's not right. It should be a sub t equals a sub 0, e to the kt. So exponential functions are used to model lots of different problems, such as bacteria growth, voltage across a capacitor, radioactive decay, and money in banking. So a sub t is equal to a sub 0 e to the kt, and exponential growth and decay problems look like this when you graph them. Your independent variable is time. Time always goes on the x-axis, and then on the y-axis is your amount. So in this case, k is bigger than 0, which means it's growing, it's exponential growth because your constant is positive. K represents your constant, just like in direct variation problems. K is your constant, it's just like that with these problems as well. So if k is less than 0, it's a decay problem. A sub 0 is going to represent your initial value, and you should notice we have in each of these cases a k sub 1 and a k sub 2, and in these cases on the graph, k sub 1 is bigger than k sub 2. And when I say that, what I really mean is the absolute value of k sub 1 is bigger than k sub 2. So if you look at the first graph of exponential growth, k sub 1 is growing at a much faster rate than k sub 2. And when you look at the second graph, k sub 1 is decaying at a much faster rate than k sub 2 as well. So even though k sub 1 would be a smaller number, the absolute value makes it bigger. Let's see, what else? A sub 0 is the initial value. It's what you always start with. And the change is always faster for k1 in that case. Okay, so exponential growth and decay are two-step problems, just like direct variation. So the first step is to solve for k by taking the log of both sides, and then we're going to take k and plug it back in. So then the second step of the equation is to solve for your unknown. You're usually going to have an unknown of amount or time. So if the unknown is the amount, you just solve it like algebraically. If the unknown is time, then you're going to have to take the log of both sides and solve from there. So we'll do an example. The number of bacteria present at noon was 400, and 9 hours later the bacteria numbered 800. Assume exponential growth and find the number of bacteria present at noon the next day. So we'll start with our equation. We know noon is the time that we started, so that's going to be t equals 0. So a sub 0 is going to be equal to 400. T is 9 because it's 9 hours later, and the amount after 9 hours was 800. We'll use this information to find k. So 800 equals 400 times e to the k times 9. We'll divide both sides by 400. 2 is equal to e to the 9k. At this point, we'll take the log of both sides. We're taking the natural log because we're dealing with e, so we end up with 9k is equal to 0.693. Divide both sides by 9, we get k is equal to 0.077. So now we have our constant, we can plug that in, and then we can use the rest of the information. So we've got exponential growth. We know that we started with 400, so the a sub 0 is not going to change. K is 0.077, and we want to know 24 hours later because it says noon the next day, so time is going to be 24. So our unknown is a sub t, or a sub 24, which equals 400 times e to the 0.077 times 24. So we just work that out on the calculator, and we get 2,539 bacteria. When we make a graph of the problem, we know that we started at 400 and that it's exponential growth, and that's basically all you need for the graph. Okay, next problem. The number of bacteria when the experiment began was 1,200. After 100 hours, there were 2,700 bacteria present. Assume exponential growth and find the time required for the number of bacteria to increase to 30,000, then sketch the curve. So we start with our equation. A sub 0 is 1,200 and t is 100. A sub t is 2,700, and we're going to use that information to find k. So 2,700 is equal to 1,200 times e to the k times 100. From here we solve. We divide both sides by 1,200. So we get 2.25 is equal to e to the 100k. We take the natural log of both sides. So we are left with 100k is equal to 0.811. And from here we divide by 100. So k is equal to 0.008. So we know k is 0.008, and then we need to find the time required for the number of bacteria to increase to 30,000. So we know that 30,000 is going to be our amount, and we need to figure out what t is. A sub 0 is going to stay the same. It's still going to be 1,200 because the amount you started with doesn't change. So 30,000 is equal to 1,200 e to the 0.008 t. Divide both sides by 1,200. And we are left with 25 is equal to e to the 0.008 t. We'll take the natural log of both sides. And we get 0.008 t is equal to 3.22. So time is 402.5 hours. So at this point I need to make a little side note. Because we do so many calculations throughout the problem and we're rounding throughout the problem, it's very possible that your answer is not going to match the answer that's in the book. So just know that if you get an answer that is similar to the answer in the book, that is sufficient. Knowing when to round and where to round is kind of tricky, and so getting the exact same answer as the answer in the book is going to not always happen. Since exponential growth and decay are kind of speculations about what's going to happen in the future, it's okay to have an estimate and not an exact answer. So when we graph this one, our initial amount was 1,200 and it's exponential growth. So that's what you need to know. Okay, next problem. The amount of substance initially present was 400 grams, and after 90 hours only 380 grams remained. Assume an exponential decrease and determine the half-life of the substance. Make a sketch of the graph. So even though this is an exponential decay problem, we still use the same equation. The only difference is going to be k. Instead of being positive, it's going to be negative. So our initial value is 400. Our time is going to be 90. And our a sub t is going to be 380. We'll use that information to find k. So 380 equals 400 times e to the k times 90. Divide both sides by 400. 0.95 is equal to e to the 90k. Now we'll take the natural log of both sides, and we're left with 90k is equal to negative 0.051. Divide both sides by 90. And we get k is equal to negative 5.67 times 10 to the negative fourth. We'll plug that in for k in the next problem. Now it says we need to determine the half-life of the substance. So half-life is when you have half of what you started with. Well, we started with 400 grams. So half-life is when our amount is going to be 200 grams. So because it's half of 400. So we'll take that 200 grams and plug it into a sub t. So 200 is equal to 400 times e to the k. Now our k was in scientific notation. We need to put it in standard form. So negative 0.0006 times time. Now we're going to solve for t. So divide both sides by 400. E to the negative 0.0006 t. Take the natural log of both sides, and you get negative 0.693 equals negative 0.0006 t. Divide both sides by negative 0.0006, and we get t is equal to 1,155. We sketch a graph, and our graph starts at 400, and it is a decay problem. Okay, next problem. A radioactive substance decays exponentially. After 100 years, 500 grams is left, and after 200 years, only 300 grams remains. Find the amount of the substance that was initially present and its half-life. Okay, so this problem is a little bit different because we don't have an initial value, which is what we're going to try and figure out. So, we know that after 100 years there were 500, and we know that after 200 years there were 300 grams. So we can plug those into our equation, and now what we can do is we can solve for a sub 0. So a sub 0 in the first equation is going to be 500 over e to the 100k, and in the second equation a sub 0 is equal to 300 over e to the 200k. Since they're both equal to a sub 0, they're equal to each other. And now we can multiply by e to the 100k and then divide by 300. So we're left with this equation. From here we can simplify. We can get 1.67 is equal to e to the negative 100k. Now we take the natural log of both sides, and we find that 0.5128 is equal to negative 100k, so k is going to be equal to negative 0.00513. Now we can take that and plug it into either of our initial equations to figure out our initial value. So we'll plug it in here. So a sub 0 is equal to 300 over e to the 200 times 0.00513 negative, and we end up with 837 grams. Now we need to figure out the half-life. So we know our initial value was 837 grams, and we know that half-life is going to be when it decreases and it becomes half of what it was. So essentially, if we take the total and divide by the initial, we should end up with 0.5. So we'll just take that and plug it into our equation. 0.5 is equal to e to the negative 0.005 t, and then we can take the natural log of both sides, and we get negative 0.693 is equal to negative 0.005 t. So t is equal to approximately 138.6 years.